Today in Chapter 10, we're going to be taking a look at the measuring energy changes in Section 10.5. So, a couple of definitions you need to be aware of, and these need to just come off the top of your head. So you're going to use them over and over again, and you need to memorize them. So the common energy units for heat are either the calorie or the joule. And the calorie is the amount of energy or heat required to raise the temperature of 1 gram of water 1 degree Celsius. At any time, I should ask you what a calorie is, and you should be able to come up with that definition. Now, if we look at the relationship between calorie and joule is what we use in the SI system, System International, for energy, 1 calorie equals 4.184 joules. And you need to know that for use as a conversion factor. Let's convert 60.1 calories to joules. And this is a common one-step conversion. The only difference is it may not be a unit conversion that you're used to. So remember the conversion we had on the last page, that there were 4.184 joules equivalent to 1 calorie. And you're just going to set it up to cancel calories, multiply, and your answer is 251 joules. You'll have to do a few problems like this. It shouldn't be any problem at all for you to do this because you've done simple one-step conversions before. It may give you joules and ask you to change it to calories, where you would just flip your conversion factor so the joules are on bottom and calories on top. All right. The energy required to change temperature of a substance depends on the amount of substance being heated, which should make sense to you because I know that you have experience cooking things, even if it's on a small scale, even if it's in the microwave. But the bigger the substances you're cooking, the more energy that's required to cook it. The next change is the temperature change that we look at. A bigger temperature change is going to give us more energy or heat. And the identity of the substance, because not all things heat up at the same rate. So here's a general definition for specific heat capacity. It's the energy needed to change the temperature of a mass of 1 gram of a substance by 1 degree Celsius. So even though we just talked about the definition of a calorie, and that's the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius, we can apply that thought process to any substance, but we don't call it a calorie because it depends on what substance. It's not water. So the specific heat capacity is going to be the amount of energy required to take the mass of 1 gram of a substance up 1 degree Celsius. This is a table from your textbook that just shows some specific heat capacities of some of the substances that you're going to be using in your calculations in your homework. And one thing I want to bring to light is the fact that there are 3 different specific heat capacities depending on the state that water is in. If it's liquid, it's going to take 4.184 joules to raise 1 gram of water, liquid, 1 degree Celsius. Whereas if it's ice, it's going to take 2.03 joules per gram per degree Celsius, and steam is 2.0 joules to raise 1 gram of steam 1 degree Celsius. Some of the others that they have down here, these are just common elements off the periodic table. Aluminum is 0.89, iron 0.45, and so on. So if we look at this, you'll notice it takes a whole lot more energy to raise the gram of liquid water, 1 gram of liquid water, 1 degree Celsius, than it does mercury, for example, or gold, for example, or even aluminum. So it takes a lot of energy to do that, and that has to do with water's polarity and some of the bonding properties that we talk about in biology. To calculate the energy required for a reaction, we're going to use a formula, and that formula is Q equals MS delta T, and I know they put SM, but I learned it MS delta T, so it's just something that comes from my mind straight out like that. So it's one of those formulas you need to memorize. And this formula, Q, is going to represent the heat or the energy required in joules. That's our unit. The specific heat capacity is joules per degree Celsius times gram. So it's the amount of energy it takes to raise 1 gram of substance 1 degree Celsius. M is the mass, and it's going to be in grams. And delta T is the change in temperature. And that's going to be in degrees Celsius, which is important to note. And the change in temperature is going to be temperature final minus temperature initial is how we're going to do that. That's nice. Let's look at an example. It says calculate the amount of heat in joules needed to raise the temperature of 6.25 grams of water from 21 degrees Celsius to 39 degrees Celsius. When we look at this, what we're going to do is start with writing down what we know and what we need to find. So we want to find Q. We know that mass is 6.25 grams. We know that the initial temperature is 21 degrees Celsius. We know that the final temperature is 39 degrees Celsius. And in order to use Q equals ms delta T, we're going to have an S value. So we have to go back up and see what we're dealing with. We're dealing with water. And water from 21 to 39 degrees Celsius is going to be liquid. And we know from our chart that the specific heat capacity is 4.184 joules over grams times degrees Celsius for liquid water. So let's plug in what we have and find what we want to find out. So we start with the mass, which is 6.25 grams. We're going to put in the specific heat, which is 4.184 joules over grams times degrees Celsius. And our delta T is going to be temperature final minus the temperature initial. So temperature final is 39 degrees Celsius minus our initial, which is 21 degrees Celsius. And that's going to allow Celsius to cancel here and our grams to cancel, and that leaves us with joules. So let's simplify it a little bit. That's going to be 6.25. We're going to drop the units now that we know everything's going to cancel right. And right now, 4.184. If we take 39 minus 21, we're going to get 18 degrees. We're going to multiply those three together, so 6.25 times 4.184 times 18, and Q is going to equal 470.7 joules. Let's look at another exercise. A sample of pure iron requires 142 calories of energy to raise its temperature 23 to 92 degrees Celsius. What's the mass of the sample? And it gives us the specific heat capacity of iron as 0.45. So let's write down what we have again, and remember that it's going to be Q equals ms delta T. So it says it requires 142 calories of energy. We have the temperature initial as being 23 degrees Celsius and my temperature final as being 92 degrees Celsius. So let's go ahead and just do final minus initial. So it's going to be 92 minus 23, which is going to be 69 degrees Celsius change for delta T. We have M, and that's what we want to know is the mass. And I know the specific heat capacity is 0.45 joules over grams times degrees Celsius. And if we look at this, we notice that the one issue that we're going to have is the fact that energy down here is in joules and energy up here is in calories. And if you remember from the previous slide, the relationship is that 1 calorie is equal to 4.184 joules. And if we put that in the calculator, we take 142 times 4.184, and we get 594.128 joules. Now we're ready to put it into our formula and solve for mass. And since this is all multiplication, and you're advanced students, I know that it's easy for you to see that mass is going to be equal to Q divided by S times delta T. So we're going to go ahead and plug that in. Mass equals 594.128 joules divided by the specific heat, which is 0.45 joules over grams times degrees Celsius, times the change in temperature, which was 69 degrees Celsius. And we're going to throw that into the calculator. And we're going to get 19.13, and that's going to be in grams. So our answer in this case is going to be C. Let's take a look at the next concept check. A 100-gram sample of water at 90 degrees Celsius is added to a 100-gram sample of water at 10 degrees Celsius. So the final temperature of the water is what? And if you look at this, we have equal amounts up here. So we have a 100-gram sample here of water at 90, a 100-gram sample of water at 10, so equal amounts. So when we look at what's going to happen with the temperature, once it reaches equilibrium, and this is actually one that we saw in the textbook as well, we know the final temperature of the water is going to be 50 degrees Celsius. We take a look at the next concept check. We have a 100-gram sample of water at 90 degrees Celsius, and it's added to a 500-gram sample of water at 10 degrees. So we don't have equal amounts of water. So we're going to have to put this into an equation and take a look at it a little bit differently. If you remember from earlier lectures that heat transfer happens from warmer to cooler, you're going to notice that the 90 degrees Celsius sample of water is going to transfer energy to the cooler water at 10 degrees Celsius. We're going to use Q equals ms delta T, but what we're going to do is look at this as a combined system that has the same Q value. So whatever energy is transferred from this example of water here to this example of water here is going to be the same amount of energy. And because of that, we can kind of set up this a little differently than what we're used to looking at. We can take the ms delta T on this side with the 100-gram sample and set it equal to the other side, which is the 500-gram sample. And the reason that we use this negative sign on this side is because the 100-gram sample is losing heat to this side. So we're going to put it as a negative amount because it's losing the heat. So let's go ahead and fill this in real quick. And we have negative, and the mass is a 100-gram sample. And our specific heat is 4.184 joules over grams times degrees Celsius. Our delta T, remember that delta T is equal to the final minus the initial temperature. So in this case, on this side, the initial temperature is 90. And what I'm going to find is the final temperature, because the final temperature, once this reaches equilibrium heat-wise, is going to be equal to the final temperature on this side as well. So the final temperature is going to be final minus initial, which is going to be 90 degrees Celsius. And I'm going to set that equal to the system on the other side. The mass being 500 grams, same specific heat. And our delta T on this side, our initial temperature is 10 degrees, but we know that our temperature final is going to be the same for both sides. And because you're advanced math students again, we have all multiplication through here except for what's going on with the temperatures. So I can divide both sides by 4.184 and get rid of those because they're on both sides. We're going to get rid of those, and we're going to simplify it a little bit. We can also take both sides and divide by 100 to reduce it. So this is 1, and over here this is going to become 5. So that clears things up just a little bit. So what we have left then is this -1 or negative sign. So we have negative times temperature final minus 90 degrees Celsius is equal to 5 times temperature final minus 10 degrees Celsius. And it's just simple algebra from there. So negative T sub F, and this becomes positive 90 degrees Celsius equals 5 T sub F minus 50 degrees Celsius. And we are going to add T sub F to the right-hand side and subtract negative 50 and bring it over to the left-hand side. So we're going to add it to both sides. We have 140 degrees Celsius is equal to 6 times the temperature Fahrenheit. And when I go ahead and solve for T sub F, I take 140 and divide it by 6, and I have T sub F is equal to 23.3 degrees Celsius. So that would be the final temperature after these two come to the same temperature of 23.3 degrees Celsius. This concept check is very similar to the one before it. I don't have time to go through it with you. I'd like for you to try it, and if you have questions and can't come up with the correct answer of 18 degrees Celsius, you need to come see me. Big difference in this one is one side is water and one side there's going to be the specific heat of iron used. Let me know if you can't figure this one out.